All right. Hello, everyone. Welcome to the Symposium for the Network Modeling Summer School, hosted by the Center for Reproducible Biomedical Modeling. Thank you to everyone who's attended the last 4 days of classes. We hope you've enjoyed the instruction and also found it really useful. And we hope that the work shared today will expand upon the knowledge that you've gained over the last 4 days. We're going to wrap up our week-long course with talks on software and models that will be presented by 6 invited speakers. So we are honored to have these individuals join us today. Just a really quick overview of how the day is going to go. We're going to have 3 talks. Each individual will have an hour to present their research and have a question and answer period at the end of their session. We'll then break for an hour and we'll have 3 more talks in the second session of the day. We're going to go ahead and start our day with our first speaker. We'd like to welcome Dr. Matthias Koenig. Dr. Koenig leads a research group for systems biology and systems medicine of the liver, regularly publishing models in this domain. His executable simulation model of the liver is an excellent example of a reproducible modeling workflow. He's also heavily involved in creating tools that support the use of standards in the systems biology modeling community and is an active member of the Combine community leadership team. Today, he'll present his work on SBML utils, which we've seen a little bit about in the course. It's a Python package that facilitates work with SBML models on tasks such as model creation, annotation, and visualization. So welcome, Dr. Koenig, and thank you so much for joining us today.
Thanks, Veronica, for the kind introduction. Okay, I just have to share my screen here. Okay. First off, like organizatorial, there's a bit.ly link here on this page. If you just go to bit.ly SBML utils -tutorial, you should get access to the slides. And because there are some links in this document, and it's much easier if you just can click on your own links than having to type everything from the slides. So without further ado, today I will present SBML utils, Python utilities for SBML. Perhaps a few more sentences about my background. Originally I started as a computational modeler, I would say, or like in my PhD, my main task was to create a computational model of glucose metabolism and glucose regulation in the liver. At that point, I had no clue how to do modeling, and I had no clue how to build proper models and so on. So it was, I would say, it was a long journey from there, from nothing to where I stand today. I would say like the main issues were like definitely like reproducibility and also reusability of models and so on. But this is at the beginning of my PhD, I had no clue that these are the big issues, and the big issues which will bite me in year 2 and 3 of my PhD. But I learned on the way. I started perhaps I will start with this. Yeah,
real quick. I went to SBML utils dev tutorial, and it's Google Slides, but I need access.
But yeah, everybody should. Okay, you deck. Lucian. So I just blocked you. You know.
Oh, that was
no, just joking. Okay. Okay. Share. Okay, good point. I shared and changed to anyone with the link. Anyone with a link should be able to comment. Done. Okay. Thanks. Okay, should work.
That worked. Thanks.
Perfect. No, thanks you for the feedback. Basically I started with today I have a bit more time, so I would use it to tell a lot of anecdotes. So I basically started with MATLAB and like encoded everything in MATLAB. And at that point we had a university license to do that. But later on we didn't have licenses anymore, and I was also like didn't have money to buy licenses, so it became really problematic even to rebuild on my own models. In addition, in MATLAB and so on, it was really easy to just write equations down and get something which simulates as an ordinary differential equations. But later on, it turned out there were lots of rookie mistakes in the model, like things like mass balance via transport processes with different compartments and things like that. So there's lots of complications in there, like that you have to take care of amounts and concentrations and what are your rates and so on and so on. And to do this all correctly, like without any restrictions on what you are allowed to do in for instance, MATLAB, it's really complicated. And basically, as expected, I failed in that, but I didn't fail too bad. So like, let's say that the model, like the main results are all correct, but numerically they are not really reproducible. Well, they are reproducible, but like in just if you write basically the wrong equations. Let's say it like that. Okay. Yeah, and that yeah, on the way, like basically then I published the model, and in the like, well, I thought if I publish it, I submitted it, and then in the review process, like suddenly I heard the first time about SBML and model exchange standards, and that other people thought about that. And so the reviewers just said, hey, please put your model in this standard format. And that's what was my first interaction with SBML. And like basically, I tried a lot. It was a steep learning curve at the beginning, but yeah, I learned a lot on the way. So yeah, years later, we're now here at the SBML utils and Python utilities for SBML. And I'm an active contributor to the SBML community, and yeah, even an SBML editor. And I believe in the standardization, and that this is the only way to build good and I say like reproducible and say believable models, I would say. So yeah, what is SBML? I don't know how much you heard already about this, like, but for understanding the SBML utils, it's important to have a bit of background. So this is basically a standard language to describe, I would say, mainly ordinary differential equation models, but there are extensions for other model frameworks. It consists of a core language, which is mainly, I would call it process entity core. Like it's called in SBML more like species reactions, but I would say like everything which fits well in a process entity paradigm can be put into the core of SBML. Yeah, there's additional packages. I would say they exist around 10 at the moment, like in different states of development. I would say the most important for me as a person coming from metabolic modeling is like FBC, it's constraint-based modeling, COMP, which is hierarchical model composition, if you want to couple models of different scales, distrib to handle information about distributions, and also uncertainties, for instance, in experimental data, and then groups and layout information. Yeah, many tools are supporting that. And this is also like for somebody who is starting with modeling, I would say this is one of the biggest selling points, because you can't develop everything on your own. Most of the time you can develop a model, or you can develop a bit of software, but yeah, if you develop a model, you can't develop ODE solvers, you can't develop visualization software and so on. It's just there's not sufficient time, like for instance, in a PhD or in a master's period. And so it's very helpful, like if you just develop your model in something where you have a large ecosystem of tools and for analysis, visualization, and so on. Yeah, one big challenge, and this was also the first challenge I had when I came in contact with SBML. How do I put my model into SBML? And at that point, like yeah, many of these tools didn't exist yet. Well, I don't know. This is now around 10 years ago. Like, okay, Quasi and so on existed. Antimony, I don't know. Like I think first versions of these existed also. The libraries existed, but yeah, all what I'm showing on this slide, they developed a lot in the last 10 years, got much more features and got much more robust, I would say. 10 years ago, when trying many of these tools, I said like it's not critics about the tool, but they were much earlier in the development phases and had less user and less people testing the features. Yeah, so how do you create an SBML model? I would say there are now more and more text-based formats. There are things like Antimony, SBTab is there. There's also like there came a new format right out now, like mainly for rate rules. But there are a few text-based formats where you basically can open a text editor and write your equations or your systems, and this can then be translated into SBML with a tool. I would say Antimony is probably what you know. Yeah, but this approach has certain limitations. would say it's often you don't have validation and no, let's say no help. Like you basically have to understand how this format looks and how is the syntax of everything. And actually you have to, yeah, it's difficult to figure out what you can do and what you can't do. It's more like you have to hope there's good documentations, there are good examples and so on, and then learn from these examples by doing. And hopefully you don't get too cryptic errors on the way, because often like it's with this stuff, it's like it's either working or you get a very cryptic error and you're a bit on your own with that. So yeah, this works very well for small models, I would say, and small models, not too complicated constructs, and using basically the core packages. Then are there graphical editors, Copasi, Cell Designer. There's also I think BioUML. I don't know how it's called. There definitely another tool from Russia. There's a tool from Chris Myers. I also forgot. iBiosim. Exactly. There are a few graphical options, but yeah, they are often difficult, I would say, to interact, and especially like you don't have programmatic access to the things. I would say this is also pretty good for very small models, or if you have a model and want to modify it a little bit, then this is pretty good. But I wouldn't build a large model in Copasi. But I would say it's a question of taste. It definitely has a low entry point because you don't need to know much about SBML and how to build this model. You basically rely on the things you see in the GUI and then click on the information. And the last way, what you can do is basically going very low level and just using the library, basically libSBML or JSBML. But these are very, very low level. I would say they are very powerful. You can basically do everything in SBML, what is possible. But you have to write a lot of code to get your things done. And there are many silent failures, I would say, which are very dangerous. It's basically you try something, but you don't know that it didn't succeed because you don't get a raised error or you don't get a warning. It's basically you have to check return codes, which are a bit unintuitive probably for people working in Python or in some other languages. Probably people coming from C++, and this is how you do it. But here in the Python world, this is very unintuitive. Yeah, so these are basically the main options, but all of this didn't really work for me. Like I would say I'm pretty good at programming. I like to create things programmatically and basically just write the rules and write as well. I'm very lazy, so I like write as few lines and code as possible with as much support as possible. So I definitely wanted things like validation, type hinting, auto-completion, yeah, like being aware of all the things which are going wrong. Yeah, and being able to do this programmatically. Perhaps back to this initial anecdote, when I had to build my own model, like basically I also didn't know really about libSBML and stuff like that. So basically in the end, I just wrote like some custom scripts which wrote XML by hand without having the path. And so it was just like, yeah, often the entry point is really difficult to SBML. I didn't know about the libraries and it was very difficult to compile at that time. Or like I would say like now you have to just pip packages which install, everything works in Python. It's basically, and they install in 10 seconds. And but then back then you had to manually compile C++ code with Python interfaces and try to get this running. And this was basically, in the end, I just wrote some custom XML creator thing, which is not what you should do, but it's basically, if you have no clue, it's probably what you do. And you see this in many tools that they're not using the libraries, but doing stuff like that. Okay. Yeah, long story short, but this was the main motivation. Like all these approaches have legitimate use cases, but for my use case, it didn't really work out. And so I developed like this collection of tools over the years. It's basically a collection of Python utilities which allow to programmatically develop SBML models and do many repeating tasks which occur mostly in my own models, but also I would say like like in the models of my corporation partners, because often it is like you want to do the same things with models from other people, and then you basically get bugs, and this is what is fixed. So it's basically what is developed and what is fixed is based on user requests and actual use cases with models. So what is the main functionality? I would say model creation, manipulation, model merging. It has strong unit support, which was very important for me. The whole library has type annotations, which helps a lot, like in the development and finding bugs also. It has support for annotations and allows things like doing model reports and some more advanced things. For me, really important was also like support for multiple packages, and especially like the hierarchical model compositions in combination with FBC, distrib, layout, and also groups. So how does model creation now in this library look? It's basically you install a Python library, and then you wrote Python code in your integrated development environment, be it PyCharm, Visual Studio Code, Spider, or something like that. So it's more like you write Python code, which is then creating your SBML model. It's a bit like different than creating a text file or interacting with the GUI. Yeah, normally you just create a few objects within a Python module, and there are like certain fields. If you set them, then the whole program knows, okay, I should create this and this SBML objects. And you can see many of these things are very, very. I would say it's an abstraction layer around libSBML, and it allows to do things very, very concise and very, very fast. Like if you look things like here, like you basically have to set for every attribute you want to set or want to access or want to check, you basically have to write one line of code. And this is getting a lot of line of codes. So basically to do things like, okay, create a species, set the SID, set the initial concentration, set the compartment, you need at least 4 lines of code. In addition to, you have to create the model, have to set up the SBML document. Basically, there's a lot of boilerplate that you have to do in the libraries, which is taken care of here. And then you create basically your compartments, your species, your parameters, your reactions, whatever SBML object you want to create in the respective lists. And then out of this list, the model is created, and it has like some basically validations and warnings, errors, and you can create model reports from that. In the end, I will show some practical examples, run through a few examples, and by the way, if you have questions or anything, comments, just jump in. I'm very happy to answer things on the way. Okay, this is basically like, I would say, like the minimal SBML example, and this is also like how most SBML models look. They are pretty concise. They don't contain much information, but this makes it often very, very difficult to reuse. In reality, you want to do much more, especially like if your model is in, I would say, a final version, which you want to publish, or upload on biomodels, or exchange with corporation partners or other people. So normally, you should add much more information, like especially things like units. It should be, personally, I'm always a friend of being very explicit if you are in amounts or concentrations, because many of these tools, basically, they just take certain assumptions. And so, for instance, it's you have to know what the language is doing, and if it's creating amount of species, amount of concentration species, and things like that. Here, like if you're more explicit and say what, and set the flags, then I think this is a bit better practice. You can set annotations like SBO terms, additional information like chemical formulas, charges, and so on. And here you see also like, for instance, in these classes, like it's a mix of the different packages. It basically allows you to easily create all the informations on species. Normally, like, for instance, the chemical formulas and charges come from the FBC package. And in the low libraries, you have to extend your species object and set then the FPC attributes and so on. And here it's basically, you just have one object constructor where you can set all the fields, and in the background, it's managed. This information comes from this package. If I use these fields, I have to include these packages and all this stuff you don't want to take care of. It's done in the background. And then you have things like annotations to describe what is the biological and I would say computational meaning of your objects. And you can do things like nodes, and especially like nodes and things. I find this more and more important, like working or developing models over time, that you have basically good nodes where you just describe why did you do something and so on and so on. Because if you come back to the model, you often forgot, why did I model it like that and not more explicit? Why is this in here? So, and these nodes, of course, should be somehow distributed. And I noted so often like I'm just writing these nodes in the program code, and so like I should just write them on the objects, so that because in the end I exchanged the XML and the program code, so like I moved a lot of these comments directly in the SBML. Yeah, a lot of things is happening in the background, which is making this which basically tries to catch all the errors I see myself. Like one thing I often see that is I'm just using wrong annotation patterns or wrong IDs here. So there's like basically just checking of all these annotations against the regular expressions for that, and partly there's also like resolving of the actual information. This is more in like basically in the next version there will be a full resolution. So it's basically you have these annotations, but often you want the human readable information. What is the definitions? What are the names of these entries? And this should be basically injected also in the model, because it's not helping you much to read KB 4167. You want somehow the information. What is this? Is this glucose or not? Yeah. There are additional features which I often use. Like one thing is, I would say, is data interpolation. I use basically, you can use data to create splines, add this to the models. This is often something you want to do if you want to drive your models via experimental data. So you have a model and it has a constant boundary, and suddenly you get data for this constant boundary, and then you want to somehow create a new model variant, or like for the experts, if you do a simulation experiment and want to create like in the simulation experiment a model variant, then you would have to inject or like replace basically this boundary condition with a mathematical function which describes the interpolation of these data points. And so there are like some helpers for that. As soon as I have the data, I can do different interpolations, which are just becoming piecewise functions which I can inject in models. That's just because this happens often for me. Yeah. Model reports. This is, I would say, one of the key building blocks for me, like, because for me, it's always very difficult to understand what is in my model and to find information, especially if the models get larger. And in the end, it's like, okay, you have your program code, but you want also like some nice way of filtering the actual SBML objects to find what is the information in there. So some time ago, I created like a static report, which was basically just an HTML page of having all this information with a bit of filter function. But now, like in a Google Summer of Code project, we're going towards a full responsive report, which allows really to just upload an SBML model, and then you can very easily filter, search in that. Like the idea is also even create a basket where you put objects, and this is often for people if they want to understand models. And especially if they want to understand very large models, genome scale models, and so on. I will show a bit of demo in the end. Yeah, so this high-level overview what SBML utils is and can, and it's I would say it's going with two other main building blocks together. SEISML, which is a network visualization of SBML networks, and SBML Sim, which is basically handling model simulation and analysis. The nice part is all this are independent pieces which use SBML as an exchange format. And so like you can, in your own workflows, just say, okay, perhaps I'm interested in this network visualization. It could be interesting for my workflows. So you can just use the visualization part, or you're just interested in the model creation part and then want to use Roadrunner Tellurium for the actual simulations, or just create the model, load it in Copasi, and then do your parameter scans in Copasi or something. So this is very easily, because it's not not everything is. So you have the SBML as a clean exchange format between everything, and that's why it's for me also always very important to have as much support as possible for all the features in the different tools, and that the different tools are not changing the SBML, because this is really bad if you want to use other tools in your workflows and they just change the SBML. That's not good. You want just have your basically your SBML, pass it around between the different tools, but the different tools should not basically they should not lose information in all the round tripping. That's the ideal case. But currently it's more like you load things in a different tool, you do something, and then you lost half of the information you already have in the model. And then this tool is not very useful for integrating into workflows. Yeah, so SEISML is this network visualization tool. You basically can upload SBML models and then have different views, look at subgraphs, have annotation support, and so on. An SBML sim is basically the one kind of simulator. I would say this is very alpha-ish. I would say this is, but it's basically for my own simulation experiments and the simulation experiments of my students. This is very useful, but the document, like compared to SBML utils and the SEISML, the documentation and so on is not there yet. But it does many important things which I didn't find in many of the other tools. Like especially it has full unit support, the multi-core execution, and also going towards full ZML level 1 version 4 support. Yeah, I will now walk a bit in the second half of the talk through some examples. Basically the only thing you have to do to follow or rerun this example is basically you have to install SBML utils. I would say the best entry point for that is you just go on the homepage, and there's basically an installation section. I would say the best thing is to just install the development version with pip, but otherwise you can also install the latest version. But not everything I showed today is in the latest release yet, but I will make a release over the weekend, so then you should be able to do everything. Otherwise, just use the development version. Yeah, there is some documentation. Basically just click on the docs and see basically most of the feature or the core features documented. I think the most important thing is like the how to create SBML models. SBML distrib is how you would use SBML distrib in your models and create certain things. You have SBML reports, how to do annotations, and so on. But today I will mainly show examples of how to create model and how to annotate models and how this works together a bit with the cytoscape visualization. Yeah, the examples are all in the repository. So if you want to execute it, just clone the repository or download the example files directly from the GitHub webpage. And this is all in this SBML utils examples, minimal example. Cytoscape, the other tool, is basically a second link. It's pretty easy to install. Basically have to have Java 11 installed, and then you download Cytoscape, and then there's something like a Cytoscape app store where you just say, I want to install this SEISML. But it's basically described here, and if you follow the links, it should be pretty easy for you. Just install Cytoscape, install the plugin, and then you can do everything I'm showing today. Okay. Yeah, so let's get started. I showed already on the one slide this example of the minimal model. Yeah, so what you basically do is you just yeah, you basically write certain fields directly in the module, and then you can say, I want to create a model based on this package. You could alternatively create a dictionary and store this information in there. This is just it's a bit of a question of taste. Often I find it nice to just write it directly in the module level. And then you, after you wrote this information, you call basically a create function, which has many different options. the most important thing is that you just say, okay, which modules do I want to use for this model? In this case, basically, you would just say, I want to create this, I want to use this module. So you would basically say like minimal model. Yeah, in this case, I just included the full path to it, for testing reasons and so on. But yeah, it is sufficient normally to just say, okay, this is my module file, and I want to create that. And then you have a lot of additional fields in here, and then you can just execute this factory. And if you execute this, yeah, it's not much is happening. Often you get certain warnings that you should define certain things, like for instance, model units is always something very good. If you're not providing units on every object, at least put the units on the complete model to describe what are the time units and the extent substance units of your model. This makes it for other people much easier to understand, okay, what is the overall, what are the overall dimensions and SI units you're talking about in the large scale. It doesn't give you things for parameters and so on, but it helps you already a lot with the species and the reactions. And if you want to couple to the species reaction graph. And then you basically see an output. Okay, this file was created. It's valid. It was automatically checked. This was pretty fast. And then we can basically look at the SBML, which was created. So yeah, one problem with SBML, if you open it in the browser, you always see only the annotations. So you we have just to click Control U or like look at the source code, and then you see, okay, this SBML was created from this model. Yeah, in this simple model, we didn't do much. In this case, we just created a compartment which we call cell. Two species, S1 and S2, and then a certain parameter K1, J0, and so on. Yeah, this is basically everything we did. Yeah, and if you would do something wrong, like for instance here, writing something like this, and would try that, then yeah, you would see, okay, this didn't work, something is wrong. And we would get basically the mass ML consistently, the formula S3 in the mass element uses S3, that is not the ID of the species and so on. Okay, this makes sense. Okay, this is not, how I say, this is not the most user-friendly, but if you know SBML a bit, and if you are a programmer, then you will find very fast what went wrong in your definition. So in this case, it's basically the S3, and most of the time you get a very good hint what it is. It's a kinetic law with S3. So yeah, here kinetic law with S3, so something didn't work. Yeah, and then we can just easily fix that. Also, other things, if you yeah, basically everything which is invalid SBML will give you yeah, either like directly here on the field, like for instance here in this case we already catch it on the level of the library, because we know this is a required attribute. So in this case, it's not even going to the SBML validation. Yeah, in reality, there should be units on everything. And if you just run this, basically we just ignored all the units. You will see like there's basically a lot of warnings, and you should add on a lot of objects. You should add units so that the model can be completely checked. But you can ignore certain subsets of errors easily here in the creation. And so if you decide, if you make the decision to not use units, you should just set the unit consistency false, but by default, everything is unit checked. Yeah, the whole thing, like basically we created the result, and that at the same time, this can then also be visualized. Like for instance, yeah, what is happening here in the background, I have a cytoscape session open. So as soon as I create this model, basically the model is sent to cytoscape in the background, and we can see the visualization here of the model. There are certain graphs in here. I think the most important is the space element, which is the species reaction graph. Yeah, and we see that basically the information is in here. We had a reaction S1 goes to S2 with a kinetic law K1 times S2. We have certain initial concentrations and so on. Yeah, one thing you definitely want to do very early is, or in general, like is basically doing annotations. I'll just move this a bit to the side. And yeah, so there are different ways to do annotations in SBML utils. I would say like, yeah, one very nice way is just use an external annotation file where you just write the annotations in there. Yeah, often I just use an Excel file to collect annotations, and then you basically have different columns. Everything which is not starting with a hashtag is one entry of annotations, and these are mapped on the model. Yeah, so you just say, okay, you can define which subset of objects should be annotated. Should it be a document level, model level, on compartment, species, and so on? You have different types of annotations. Most of the things are RDF, but we can also annotate things like formula and charges, which are written as FBC attributes. And we can basically writing the qualifier, what it is, or does it have the tags on, and so on, and writing like the resource. This is mainly, I would say, mostly identifiers or org resources and terms. Exactly, and then you can, yeah. The interesting part is you can use patterns. So you can just write, instead of like, I just want S1, you could write a regular expression. For instance, all my species, which are S and one or multiple digits. If this identifier is a species and follows this pattern, then it should be a simple chemical. So you don't have to write everything out, but if you use certain patterns, for instance, for your parameter, everything which is starting with K and so on, you can measure the Lenten constant and so on, or Km and Vmax. You can just annotate whole bunches of this models, of this objects. And it's pretty easy. You just then reference the external annotation file, rebuild the model. Okay, in this case, you get, please ignore these warnings. This is just, okay. This won't be in the next release, but it's just for me for debugging. Yeah, then you get basically a new updated model. In this case, I overwrote this minimal model, and if you now look at the SBML, we see that we have all the annotations in there. So for instance, yeah, we wrote this SBO terms, and yeah, for instance, for the S1 and S2, we wrote the SBO terms via this pattern. So this was resolved, and all these annotations are in there. So I would say this is pretty easy to do. This is exactly, this is pretty easy to do. Alternatively, instead of using such an external file, you could also directly write the annotations on the objects. Perhaps I will just show the updated model. Okay, when we now updated the model, of course, we also have the annotation information here in SBML utils. So you can directly see, okay, what are I have the SBO terms, and certain information is also retrieved. Like this will become much more, that basically the annotation information is retrieved. For instance, if you have KB terms, you can automatically load the structure formulas. To show some other examples here, for instance, the repressolator. If you have things like a protein, you can of course also like retrieve the UniProt information. Okay, what is this proteins? What are synonyms? What are the functions, and so on? And this is of course much more helpful to have something like tetraglycerine, repressor protein, class B, organism, gene, instead of just knowing this is P04483. And this is, yeah, this I would say is now coming more and more, and one of my priorities to work on. So basically resolving all these annotations and getting all this information to communicate it. Yeah, an important piece is also this this model report. which allows basically to upload the SBML model. So this is very alpha-ish still, but we could then just upload such a model and would say, see, for instance, this was this mini model S1, S2, which we created. We can also see the annotations are in here. The actual information still has to be resolved. Yeah, what this model report allows, I will just show an example, the repressolator. It basically allows very easily to get an overview over what is in the model and to filter for certain things, like, okay, what are certain parameters, also what is all the math, and what are the reactions equations, which reactions are reversible, and here in this case everything is irreversible. So this is often like a good entry point to understand models and get more details about things. Yeah, this will be, I'll say this is just the first alpha version, like for instance showing here px, and then you can navigate between this species is a reactant in this reaction, go there, go back, and interactively like also navigate and understand what is going on in the model. Yeah, this will basically, like I said, this is very alpha-ish. This will be much more interactive, and this will also be more integrated with a network visualization. The nice thing about this cytoscape is that it's all about REST APIs and also Python, and here this web service is about REST APIs. So everything is basically communicating via REST APIs. So one could imagine basically how it will be that you basically can just select certain subsets here, get all the information. This is selected automatically in the network, and so on and so on. So this could all be integrated much more, like that you have there's different tools which can communicate somehow, but are independent. And they basically just exchange the SBML and have like some communication possibilities to synchronize state of, okay, what is our subsets which are selected and so on. And one could even like, there are some crazy ideas, like one could even imagine like doing things like in Visual Studio Code, writing a plugin. If you on the code, clicking on a variable, that you basically get immediately the network view, and then integrating the code with the actual network visualization and stuff like that. Yeah, so but this is also a bit more the bigger picture, that all these things should come closer together, and that you get easy overviews over the model and how this works in the network. Okay, yeah, this was basically one of the minimal examples. One with the exchange, I showed a bit the annotations. Yeah, one can also easily use this to annotate existing models. You would just load an existing model and use your external annotation file with the patterns to annotate the model, and yeah, and then you could use something like libomicsmeta to create your turtle files or whatever. The idea is also using libomicsmeta directly here to basically having external annotation files, which are then written as standardized external annotation files. But I need like a bit of abstraction layer to easily create annotations. Often such an Excel file is much more easy to handle than something programmatically. Okay, this is basically the external annotations. Is also pretty simple. Just use a model, use this external annotation files. Or in this full model, you can also, of course, if you create this objects, you could either like directly write SBO terms, which are also promoted to CV terms, to let's say first-class annotations, or you yeah, or you can directly just set the annotations fields, which is the same like using similar to an external file. Often, like for the annotations, I have to say I find it better to manage them externally, because this is not providing you much information about what it is. Unfortunately, if this would be more human readable, then it would provide you information. But this abstract things here you can also manage outside without losing any value here for your model objects. Okay, but one can see this is a bit more complicated. It's basically the same example like before, but a bit more complicated. You have like a lot of nodes. You can set basically a lot of annotations. You could define uncertainties on this object. Yeah, also you can do things like setting compartments and reactions. A lot of things which are important in certain contexts, but are often not supported by all tools. Yeah, and here also like direct integration with the flux balance package and so on. Exactly, this is a bit more full example. I wanted to show like a few two options for model composition, which I often use. The simplest thing to do model composition is just define your different parts in different modules and then put everything together. Let's say like this. This is basically, I don't know how it's called. This is not real SBML composition. This is just you have multiple information which can override each other, and you put everything in together in the end to create one SBML model. This, for instance, we're doing in this case here. We're creating a model composition out of two definition files. This one definition file was our minimal model, which was a reaction S1 to S2. In case here, this was basically our minimal model here, which we had S2, and now we want to extend that or couple it to something else. So we say we have a second model, which should be all of this model here. But in addition, we want to have like an additional parameter K2 and a supply reaction, which provides S1. And then in the end, we just say create our models. And now we say, okay, just use this two definition files to create one model out of that. And this makes often sense if you reuse things, like for instance, if you reuse units or if you reuse certain information, then you can just split it and keep this file sizes pretty small and understandable. Yeah, so like now we basically created a composite model out of these two. Exactly. The other model composition is really via the comp model extension. This is a bit more complicated, and I will show it in a second. Yeah. First, one of the, yeah.
Really quick, would you be able to end in like 3 to 5 minutes? Just so we have a couple
no
minutes for
problem.
questions.
No problem. Yeah. Just ask. Exactly. I will just will quickly show this programmatic part. It's basically yeah. Now, because you have a full programming language, you can just programmatically create all your objects. So in this case, you can create a simple linear chain. Yeah, you define again one compartment, one initial species, but then you just do a loop and say, I want to create additional species, additional parameters, and additional reactions, which just follow this pattern. And so it's basically instead of, you basically have the same code to create 20 species, then you would have to create one species, because you can have simple loops and simple if conditions and so on to programmatically create your model. Something like this is just not possible in a GUI or in a text-based format. You could programmatically create your text-based format, but yeah, okay, this is something different. Yeah, and then you can very easily, it's not much more code than before, create a long linear chain here of things which are connected. Yeah, and now you could, yeah, now I will use this chain to create a composite model. Basically, now I have a long transport chain of substances which are transported through the system, and I have my minimal model, which was just using one species and converting it irreversible in another species. And now I want basically at every step in my chain just to have this additional submodel. And so we can do this with a comp model. And here we already have our minimal model defined, which we want to couple. So we just have to define the top model. In this case, basically I'm creating a grid of species. These are basically my all my species I have. Basically, I have these reactions which are connecting the species. It's a bit of different equations. It's also a linear chain which is transported via diffusion, very similar to this linear chain here. And then I just say I want to couple my subsystems. In this case, I just say, okay, what are my external model definitions? This is the minimal model I want to use, and I want to use it basically in this case 20 times or 10 times here, and I want to couple it. I basically want to couple all them all in the same compartment, and I want to replace this species with a respective S1 species. And that's basically all there is. We couple the compartments, we couple the submodels, and then we and now we have an error. Oh, this is not good. That then exactly. And so probably I blah 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 blah. Child replaced. Oh yeah, okay. This is a classic problem with SBML because I now extended the submodel with annotations. I have their meta IDs, and of course I need also meta IDs on the top model. This is like one of the subtleties of SBML. So basically, we just need a meta ID to set here so that the submodel can really be replaced. And then this should work, hopefully. Okay, I will show this another time, but this is the basic principle there. Sorry that this example doesn't work, but it's it's basically the problem is here in the submodels, the replacement must be very similar to what is in the top model. So exactly the minimal model has to be compatible to the top model. So I will just create the minimal model without the annotations. Then it shouldn't have meta IDs, and then probably the comp model will also build. Yeah. Okay. Now. Yeah. This was basically just you need compatible meta IDs on the subsystems, and then we can see now we have this this linear chain where we have at every step basically our minimal our minimal models coupled to everything. So basically we use the model and coupled it. Okay, sorry for the delay. The floor is open for questions.
Thanks so much, Matthias. That was a really great talk and great tutorials as well. I think we have one question that just popped up in the chat. Krista says she spent some time using libSBML and is considering changing and rewriting her code. Is there any plan to export Spgn ML or link to Spgn Python?
Yeah, the question what let's say like okay, we basically yeah, basically, I think I wrote the Python library for libSBGN. So like, yeah, definitely we could support it very easily. Yeah, the question is what you really want to have in SBGN. If you just want the species reaction graph in SBGN without any layout, this could be done very easily from the programmatic part. We could do an SBGN export from here. This should be straightforward, at least from the also reaction species graph. This should be straightforward. The problem is like with SBGN, it supports much more than I'm using for certain things here in the visualization, like for instance, protein modifications and so on. And so it would be a subset of SBGN, but clearly species reaction graph and so on, that it could be written in layouts and also in SBGN and so on. This shouldn't be too complicated. But there are automatic converters for that also on the, what's it called? It's, I don't know. It's the something converter suite by Nicolas Rodriguez and so on. It's basically an online collection of where you can convert everything into everything. And there's also like, let's say like with many limitations, but there's definitely a simple SBML to SBGN conversion which works right now.
Someone else asks how to connect cytoscape with Python in general and Jupyter notebooks in particular, perhaps.
There's a package which is called PyCytoscape.
Yeah, I found Pi 2 Cytoscape. Is that what you're using?
Exactly. This is
Okay.
what I'm using, and I say this is very this is very interesting, and it's in the end it's pretty easy to connect the things. You basically get a Cyrus client, and then you send basically you send REST. You can either send REST commands directly to Cytoscape, which is really interesting, or you could you have an abstraction layer which has certain methods to send it. Cytoscape itself has an command API where you can then export functionality as commands. This REST communication is really interesting because you can basically just build a web page where you have links, where you could say, load my model, lay out my model, display data, and so on. You just click the link, and if you have Cytoscape open it out, it's really very similar to what I did right now. Like if my model is finished, just show it, and you could have a web page with links, which is doing exactly that. Yeah, this is, I would say, the main communication. I used it for very interesting. You can basically everything you can do in Cytoscape you can do. I used it, for instance, for things like I have dynamical simulation results and just map it on the node edges, node sizes, and so on, and do some dynamical graph visualizations very easy from kinetic simulation results. In total, very powerful. There's also REST client, an R client, if you're more like an R person. Yeah.
Do we have any other questions? People are welcome to unmute their microphones and ask directly if you have them.
I would say perhaps I've just ask if you want. Otherwise, I will just tell at the last minute a bit of things. I think the big challenge is like to make this all work together, and also like the integration with other tools, because currently many of the SBML tools, they only support a certain subset and so on, and so it's it's often difficult to build a model which works with all the different tools. Like so, for certain things, you really have to. For the interoperability, you often have to constrain yourself in the things you use in an SBML model, but there are additional layers of very important information which you can just put onto your models, and it gives you just additional value without harming anything. And I would say like annotations, annotations, layouts, grouping, also like units and so on. These are additional layers which make your model much more valuable. And they work basically with every tool because most of the tools just ignore this information. So it's other things like if you use, for instance, certain mathematical constructs, then you can get into problems that other simulators can't execute things. Delays is probably one of the most famous examples for that, which almost doesn't work in any simulator. Yeah. Okay. Otherwise, otherwise, if you have questions, please email me. There's also issue tracker. Just try that. Often if you read code, I would say it's well documented. Actual documentations, it's always like it's lacking a bit behind the features. But if you saw something which you have no clue how I did that, just ask a question. I will add documentation for that and add examples for that.
Awesome. Thank you so much, Matthias. Hopefully somebody will follow up. Matthias definitely is very fast about responding to those sorts of requests. So, all right. With that, we will move on to our next speaker. I'll go ahead and share. All right, so we would now like to welcome Dr. Daniel Vindle. Dr. Vindle is a postdoctoral fellow working in the Data-Driven Computational Modeling Group of the Institute of Computational Biology at the Helmholtz-Zentrum München. His current research analyzes complex dynamical systems in cancer signaling as part of the CanPath-Pro Predictive Cancer Pathway Modeling Project. And he previously developed tools for the analysis of metabolomic data in the cancer research domain as well. In addition to his research, or in kind of synchronously as he's executing his research, Dr. Vindle has worked on several open source software tools that make simulation and parameter estimation of signaling network models more efficient and feasible for large systems like those in the cancer signaling research domain. So today, Dr. Vindle will present on a related topic, a data format for parameter estimation called PETAB. Welcome, Dr. Vindle. We're so glad to have you with us today.
Thank you very much for the kind introduction. Also, thanks for inviting me and the opportunity to present PETAB. Let me show my screen. No, wrong window. Sorry, almost there. You don't see full screen, right?
No, not yet.
There we go. Sorry. Right, so happy to present PETAB today, a file format for interoperable specification of parameter estimation problems, especially tailored for systems biology applications. First, I would like to acknowledge the many contributors that were part of this project. Yeah, listed all here. Without all those people, that would probably not have been possible. Let me start out with a bit of background. So in systems biology, we're mostly concerned with various kinds of usually computational models. And here is just one example shown. Details don't matter much. It would be an example of EGF signaling. This is some network, and if you have a dynamical model, each of those reaction arrows here would come with certain rate equations, and those rate equations contain usually a number of parameters that are not known in the beginning. In this case here, all those K1 to K25, for example, reaction rate coefficients that you usually don't know. There might be also all kinds of other parameters. So if we have such a model, what do? We somehow need to infer those parameters. One option is estimating those parameters from experimental data, meaning somehow tuning parameters that the model reproduces some experimental observations. This process often looks as shown here. So we do have some model in terms of, for example, differential equations, but can also be some kind of other modeling framework. And then we do have some experimental data from which we want to infer parameters. There are various steps, some of them optional, but usually we would formulate some objective function and that we use to evaluate the fit of the model to our data. We infer parameters, for example, by optimization. We would look at the model fit, and afterwards we're usually interested in assessing parameter uncertainty and also prediction uncertainty. And afterwards we can do all kinds of analysis with this model. So there are a number of tools available helping us with all these steps here. Some tools focusing on individual steps, some tools covering a broad range here. Now, one problem we have, though, is that pretty much all of these tools have their specific requirements on how your input has to look like your model and your data and whatever else you need. And this is somewhat of a problem if you want to switch between multiple tools. Interoperability is very limited there. So the key ingredients for this process are a model and measurements. For the model, we actually do have very good standards. You just heard a lot about SBML and great tools how to work with SBML models. There are also a number of other more or less broadly supported model formats like SEISML, or also BioNetGen language, and others. There's also SETML for specifying simulation experiments. But then when it comes to specifying measurements and linking measurements to your model, there's actually not so much in terms of standardization. To be fair, one would have to mention here is the upcoming SETML standard, which actually does address this problem and comes with some parameter estimation functionality. But when we started with the development of PTAP, there wasn't really too much. So yeah, as I said, it's pretty tedious and also potentially error prone to convert your measurements and observation model and things like that to be usable by a different tool. And this also limits reproducibility of published parameter estimation studies. Also, it's pretty hard to reuse any data there because as there is no really established format, people just don't publish it even in any format. You can find some data only in some plots, or you need to go through some pretty long supplementary information where you can potentially scrape some formula from some PDF document, but it's all not so much fun. So to this end, we developed PTAP to improve reusability of such parameter estimation problems, or reusability and reproducibility and interoperability of different tools. Typical setup, PTAP was designed for is the following. So we have some model of some biological system, like some chemical reaction network, or also some other system of interest. And we do have some experiments from which we derive measurements. So usually your measurements are not from one single experiment, but you often would apply some perturbations to get some dynamic response of your model, which is much more informative for parameter estimation. So to this end, for simulating these different experimental conditions, you will need slightly different models, or potentially the same model with different model inputs. And this is what is shown here, that you will probably have some slightly different instances of one generic model. And this model is then linked to the different experiments via some observation and error model. The observation model pretty much maps your model states or whatever model entities to your measurements. So in a simplest case, this can be just one specific model state. It can be, as shown here, some scaled version of it, or it can be like any complex function of your model entities. And if you're doing some statistical inference, then each of your observables would also come with some error model that you would also want to specify then for each measurement. Yeah. So if we have this model and observation model, we can simulate the model, compare it to the actual experimental data and compute some likelihood or residuals, and then apply, for example, some optimization algorithm to find parameters that minimize residuals or maximize the likelihood. Yeah, so this is pretty much the setup we want to address with PTAP. And now coming to PTAP as a file format, it's actually a bunch of files shown here. So there is some models specified in SBML. So we're not reinventing the wheel here, just leveraging existing standards. This defines your biological system, and Then there's a number of TSV files. Just as a brief overview, one that defines your different experimental conditions. So specific model inputs, or that lets you account for different perturbations or different environments or cell lines or something like that. Then there's a file for defining your observation model. There are measurements then, and your experimental data. And there's a list of parameters you want to estimate, and certain additional information such as parameter bounds for optimization, potentially Breyer distribution, if you want to include that. Optionally, there is some table that lets you create or define certain visualizations, and this is optional. And these files are then grouped together via some simple YAML file. I would like to give you a bit more detailed look at the individual files and guide you through the process of creating those files yourself based on a rather simple existing previously published application. This is modified version of model and data that was published by Böhm et al. Already a couple of years ago. Back then, not in the PE tab format, but I think it's a nice example. So usually you do have your model already defined, and then you want to estimate certain parameters. So in this case, the details of the model here don't matter too much, but as a quick introduction, the model describes here two compartments, cytosol and nucleus, and the number of proteins here, STAT-A and STAT5A and STAT5B. And the reactions are some phosphorylation, dimerization, and translocation reactions. The reaction equations are not shown here, but like each of those edges here would come with a with some unknown reaction rate coefficients we want to estimate. To estimate these, we do have some experimental data available. What's measured here is some relative protein levels. I will give a bit more detail on the next slide, but very much we want to infer reaction rate constants and other parameters from these data. So now how do we create the other PTAB files? As a first step, we want to define our observation model. So we have these data here, and we want to create this observables table. What we need to define there is some arbitrary ID for any given observable. So for each of those plots here, we would define one observable. So here we measure the relative level of phosphorylated STAT5A, and here of STAT5B, and here the relative abundance of STAT5A phosphorylated or not. So for each of such an observable, then we would write one line. It would be one line in the table. It's just here wrapped for to fit it on the slide. We can give some more descriptive observable name where you can put arbitrary strings. This is somewhat limited to identifiers like no spaces, no special characters. We then define the actual observation function where we refer to different species defined in the model. So for example, here this PA is something you can see here. And pretty much here we calculate then the fraction of those phosphorylated species compared to the total STAT-A levels. Details don't matter much, but we provide some function here linking model states to the measurements. In addition, we define which our noise assumption. So we would assume here the measurement error is normally distributed, like additive normal. And then we define here with this noise formula, this would be the standard deviation. We could write some numeric value here or some parameter. In this case, it's a parameter that we can later override for each specific measurements, as you will see in the next slide. Yeah, as I said, we assume that these measurements have been are linked to some specific experimental condition. So we quickly want to define that in a separate table where we put some more or less arbitrary condition ID, some potentially more readable name, and then in additional columns in this table we can write some parameters as defined in the model. In this case, it's the concentration of some stimulant that was used in this experiment, and we can set here some concentration. For this example, there is only one condition, but you could imagine there are now multiple rows here with different concentrations of EPO. Now, having that, we can write down our actual measurements, like what we have here. One data point here would be one row in this table. We reference this observable ID we defined just previously. Then the simulation condition from here, this EPO simulation shows up again here. Then this is the actual measured value for the respective observable at the time point specified here. And then we specify the noise parameter. Again, here you could write some empirical standard deviation, like just some numerical value, or you can also specify some parameter name. In this case, it's a parameter which we want to estimate also, which we want to estimate from the data. Will become maybe clear a bit later. We do that for all our data points here, so just the different observable IDs, different time points. It's actually relatively simple. Once we did that, there are only two more files we create. One is the parameter table, in which we list parameters we want to estimate. So here, just for reference, I'm showing the rate equations as defined in the SBML model. This is not a separate table. It's just to be clear to which parameters we're referring here. So there you see those different K something parameters. These we want to estimate. So we would list them in another TSV file or table. In the parameter ID column, ignore the first parameter here, it's not shown. This is only a subset. Maybe here for this KX hetero, which is shown here, we can define some parameter scale. What this does is pretty much specifying whether you want to optimize your parameter in log space or not. It has previously been shown by several people that this is actually more efficient if you optimize in log space. So this you can do here, or otherwise you would write lin instead of log10, or just leave that out. You define some lower and upper bound for your parameters, and for the estimated parameters, you would put a 1 here in this estimate column. And if you don't want to estimate a parameter, you put a 0 here and instead specify some nominal value. So this gives you a possibility to easily fix the parameter or estimate it, or do back and forth. Here you can also see some additional parameters. These SD parameters are the ones we specified here in this measurement table. So we can also estimate noise parameters. It's just the same as the other rows here. We define some parameter bounds and parameter scale. With this, we're almost done. You group those files we created previously together in such a relatively simple YAML file. These are just the file names we chose there arbitrarily. You can freely choose your names. You link the SBML file, the observation, the observable table, the measurement files, and condition files. And yeah, then we have pretty much this set of files I mentioned before. Right. So this is what I will say here to the file format itself. I'm happy to answer any further questions. There's also much information available online. Just quick summary, what I would consider the strength of the PTAB format is that it's relatively easily editable. Like you can edit at least the TSV files in any spreadsheet application of your choice, or also programmatically using your favorite programming language and libraries. It's pretty much platform independent, like at least not tied to any specific programming language. It's text-based and thereby rather version control friendly. It's relatively scalable, like you can represent some rather complex problems here. For example, in some applications, we had then 10,000s of measurements and several thousands of experimental conditions and hundreds of observables or something. So this you can also represent here. It does get more complex then, but it works. Especially for more complex applications, it's nice that you can specify your problem with rather little redundancy through this specification of rather general observables, and then creating like condition-specific or measurement-specific instances thereof. And it's relatively easy to change things back and forth. And yeah, I think I mentioned optimization a couple of times here, but like the whole setup is not specific to optimization. You can also use it for any sampling-based approaches. Yeah. Now, as I mentioned, one goal was interoperability. So the probably even bigger strength or more important point is that PTAB is supported by a number of different tools. Those are listed here. It's currently 9 tools. You may or may not know some of them. I will quickly go over them. Amity is for model simulation. Copasi is for probably most well-known tool with some nice GUI for creating models, performing parameter estimation, model simulation, all kinds of analysis. There's D2D, a MATLAB-based tool for creating models, for performing parameter estimation and certainty analysis. There is DMOD with very similar functionality, but in R. Then there's Mago, MATLAB tool again for optimization. Yeah, MATLAB I mentioned. PARPy is also focused on parameter estimation in C++. PyABC is actually more for approximate Bayesian computing. PyPesto is general purpose Python parameter estimation toolbox, and there is SBML to Julia, as the name says, implemented in Julia, parameter estimation for SBML models. These tools support PTAB to a varying degree. Not every tool supports every feature there. You might have to check then specifically for your problem which one works. But nevertheless, this is actually a pretty nice selection of tools. Like with any other format, you probably couldn't use more than one or two tools without completely restructuring your data. Additionally, I was very happy to hear that it's planned to support PTAB in SBStode. That would be a great addition to the list here. Yeah, in case you are interested in getting more information on PTAB, you can find all that online, ptab.free2docs.io. That will guide you or lead you to a number of resources. So here you can, for example, find then the more detailed specifications. So there are a number of features I didn't mention here because I think it's potentially too overwhelming at the beginning, and you might not even want to use those. Then there is also some tutorial. This is actually the example I showed is taken from this tutorial, but there are some further details, and you can look at it then in more detail. Yeah. Some additional resources you might find helpful. The tutorial I just mentioned. There is GitHub repository which contains a number of example problems specified in the PTAB format. This is based on an earlier publication of some parameter estimation problems. The original focus was to provide a collection of benchmarking problems. So in case somebody of you is developing new optimization algorithms or simulation algorithms or whatever, this might be a nice resource to find some problems you can easily use, all in the same format. Can just run your algorithm over those, benchmark your tool on more than just 2 examples you otherwise would implement manually or something. So this is quite nice. Also, it can give you a demonstration of which use cases PTAB can cover. Yeah, when writing those PTAB files manually, it's not unlikely that you will introduce some errors. That happens every now and then. So in that case, our validator tool might be very handy. It's a Python command line tool you can run over your files that should give you some good idea of what's going wrong, or at least that something is going wrong. In addition, we have some visualization tool. It's at a rather early stage, so I didn't go into detail about those on those visualization files. But if you do have those, you can visualize them with this tool. Here's a screenshot. It's some Qt Python-based application where you can then go through some different plots defined there, zoom in, zoom out, get some additional information that can be quite handy to get a quick overview over any data of such a problem. And you can also overlay data and, for example, simulation results from after your parameter fitting. In addition, there's a Python library which contains functions for validation, visualization, for creating combined archives from your Python files. Sometimes it might be preferable to have everything nicely wrapped up in a single file instead of having this handful of TSV and SBML files. And then in addition, we do have some test suite, which is probably only of interest if you're developing some tool yourself, where you might want to use where you want to implement PTAB support. So this test suite comes with a couple of very simple example problems, testing specific features, and gives you some expected results for each. Yeah, all those tools and codes are available open source, permissive license, MIT in this case, but yeah, you can pretty much reuse and do with those tools whatever you like. A couple of words on PTAB development. So we are aiming at rather open development driven by community needs. Most of the communication is happening via the various GitHub repositories. So you feel free to post any issues there, and also feature requests or whatever. We are happy to hear what else might be needed. Doesn't mean you will get it right away, but we're very, very happy to hear if people have some different use cases that we didn't really consider so far. yeah, nevertheless, we need a bit of structure in managing PTAP development, and so we have we have our first editorial board, which was elected early this year, consisting of 5 members, shown here. Members are elected by the community, and so everybody is free to join there or apply to join there. And we're regularly changing. So the next open position will be there next year. Yep, right. In addition to our GitHub trackers, we also have a mailing list where there is not so much traffic. So most of the communication happens via GitHub, but important announcements will be made there. A link is included in the last slide. I would like to also mention some future extensions of PTAP that we're discussing currently. So we're working on version 2 here, and one important feature, or probably the most mature one that is currently under discussion, is extending PTAP to be able to specify model selection problems. Maybe as a bit of background, so model selection usually would mean that you don't have one specific model for which you want to estimate parameters, but you often do have some structural uncertainty in your model. So you're not sure whether a certain reaction is actually taking place in your given situation, or you might want to compare different candidate models. For example, we might have here this model with all those 4 reactions that are known to happen under some situation, or would be plausible that they do exist, but you're actually not sure if this is the right model, or any of these simpler models which contain some subset of these reactions is more appropriate to describe your data. Or let's say you want to see whether the data has evidence to favor one model over the other here. And so from the PTAP perspective, what we would like to have there, in addition to what I presented, is the option to specify such candidate models, potentially by giving such a comprehensive model and then specifying certain constraints to derive these candidate models, and then perform certain optimizations and compare the different results based on certain statistical criteria to then exclude or keep certain model hypotheses. If you're interested in that, feel free to talk to us. There is some information also available online, but we hope that this is something we will finish by the end of this year. Another point we would like to address. So far I mentioned that PTAP is built around an SBML model. This is often convenient because SBML is very well supported by many tools. Nevertheless, there are some applications where you might want to use different models. So we're drafting some extension to work with rule-based models, focusing probably on the BioNetGen language formats, potentially also PySB. This will be helpful for certain types of models. An additional point is integration with biosimulators and biosimulations frameworks. You will have another talk later, I think I saw, where this will be introduced. So pretty much biosimulators gives you access to a wide variety of tools via some well-defined interface for model simulation. And we're in discussion to extend that also to not only model simulation, but to parameter estimation. And related to the biosimulators framework, there's then also biosimulations, like this web service that lets you run simulations in the cloud. And here the same, like that would be pretty great if you could also run your parameter estimation problems there. It's at a pretty early stage, so don't expect it too soon. But I think that would be a great feature if we could link PTAB to these frameworks. They are developed by the group around Jonathan Carr. That would be super nice. Yeah, another thing we're at an early stage of discussion is converging on some common file format for parameter estimation results. It's pretty difficult because different algorithms, different tools have probably very different kinds of data to report, but this would be very helpful for all kinds of downstream analyses and for simplifying comparison of results obtained from different tools. But yeah, there's still a bit of work to do. Yeah, with this, I'm already coming to the end. So I hope I gave you a good overview of PTAB as a file format for reusable and interoperable specification of parameter estimation problems. It is supported by a number of tools already. We hope that this list grows. Now, so far, it's especially for, yeah, I think optimization-based workflows, and a few tools support also sampling. Unfortunately, we don't have anything for structural identifiability on the list. We'd be very happy to also see some tool there that will support PTAB in the future. Yeah, if you will work with, if you want to give PTAB a try, so there's this validator tool that might be very handy. If you would like to implement PTAB support in some tool, the test suite would be very helpful, and also all those examples. Further information, as I mentioned, is available on our Read the Docs page here. We have a publication on PTAB from earlier this year and +CB. And I briefly mentioned the mailing list or Google group we have that you may want to join. So you will need some Google account for that, but it shouldn't be much of a hurdle. Otherwise, GitHub is freely accessible without anything, but yeah, if you have any further questions, we are very happy answering any questions or helping with any problems. Ideally, just post something on the GitHub issue pages. There are a number of people around that can help you. Yeah, with that, I'm very happy to answer any questions if there are. Thank you for joining.
Thank you, Daniel, for joining us and for such a great talk. If anybody, again, if you want to unmute your microphones and ask directly, otherwise, if you put them in the chat, I'd be happy to read off questions to Daniel.
So I put this in the chat, but I also just wanted to mention, thanks for PTAB. You mentioned that a SEISML L1v4 will also have parameter estimation. The reason SEISML L1v4 will have parameter estimation is because PTAB existed. There had been proposals in the past. They seemed complicated. We were having trouble getting 2 different groups to actually implement support for them. So when PTAB existed, then suddenly these proposals got new life. We go like, oh, hey, this is actually like someone's used this for real. I think we simplified things down. Like, is it in PTAB? It's like, yes, it stays in. If it's not, it goes out. So it was like the importance of PTAB in the existence of parameter estimation in SEISML can't be overstated, basically. So thanks a lot.
That's great to hear.
Yeah.
Very happy about that. Yeah. There was really a need for whatever well-defined file format that can be used by multiple tools. And like if you ever try to reproduce some published study of any parameter estimation task, it's extremely difficult to find all relevant information. So yeah, there was a big gap.
Absolutely. So yeah, thanks. Your model specification problem looked interesting to me. Are you thinking of having like would the SBML file have all the reactions and then PE tab would specify the subsets? Or can you imagine like having a bunch of SBML files that you just are sort of arbitrarily different from each other? Or what are you thinking?
Yeah, that from our experience, the most useful thing would probably be defining some superset and then enabling or disabling specific reactions. But we also want to allow different SBML models. So it's still under discussion and not finalized yet, but probably both options will be possible.
Okay, yeah, that'll be interesting. One of the things we're sort of experimenting with now is random network generation and then trying to choose between them. So in that case, we would probably have like the native format would be randomly generated networks. I'm sure we could probably generate the superset model also if we needed to, but that would be the first thing we had. So that's really interesting. Is there discussion on that on PE tab discuss or?
Not so much, but I can point you to some repository where there is some draft for how the respective model candidate definition would look like. I'm having some trouble accessing the chat while I'm screen sharing, but I will post the link later.
I think it's in the more section of the item.
Yeah, we also have another project which has tens of thousands of models. So a diff kind of approach might be the way to do it, rather than storing all 50,000 models explicitly as SBML, is to store them as one big model, and then you have a specification that generates the model variance from that superset.
Yeah, we found that to be most convenient way than just introducing a couple of parameters to switch on and off certain reactions or parts of the model. Makes it also easier if you do want to modify your candidates, then you don't need to modify 1,000 files, but just
right. Yeah, that's interesting. Okay. Yeah.
I guess I wonder maybe Lucian could help answer this, but what made it so difficult to create a standardized format for parameter estimation? I guess, why wasn't that implemented?
There's a lack of interest.
Okay.
Some lack of interest, and it's an inherently really difficult problem. There's a lot of moving parts. Go ahead, Daniel. You were going to say something too.
Yeah. Like the one part is coming up with some file format, but the more difficult part is people adopting it. I mean, every tool had some kind of input format. Well, sometimes it's code, sometimes some specific file format. But yeah, I think for small problems as encountered more in the past, I think it wasn't so much of a problem potentially to not have such a format. But now with increasing computing power and so on, models are getting bigger, data sets are getting bigger. And then I think the problem gets much more severe. And yeah, then you have so many different algorithms, or it depends now if you do some more statistical inference or whether you want to just use some arbitrary objective function. So PTAB can also not represent any arbitrary parameter estimation problem, but we're focusing here on those likelihood-based approaches, I would say.
So that you've struck an interesting point there, because we're trying to fit these models, and we've gone through, we use differential evolution because we found that to be the best, but every differential evolution implementation seems to be different. So we have differential evolution implementations that either can't find a solution, take 2 days to find a solution, or take 5 hours to find a solution. So in the standard, how can you specify, I don't know how we can specify which particular code was used, because it seems you can't just specify the algorithm because everybody seems to implement the algorithm differently. And we get different outcomes.
That's a good point. I forgot to mention that. So PETAP is really focused on specifying the parameter estimation problem as such, but it does not really care about which algorithm you apply.
Yeah, right.
So it's applicable for sampling optimization. You can use your local global optimization method of choice. This is not encoded here.
Oh, yeah, okay. That's probably the safest thing to do.
I mean, in general, that sounds like a Casal issue to me. Like,
right.
So like you would use
Yeah, but
Casal,
it's not...
like your root term would be like differential evolution, and then each individual implementation might get your something more specific that then you could reference. Say like, we use this one. Use this one if you can. And then if someone doesn't have access to that, then they can use the other one from the root or something.
Because we've seen marked differences between implementations, all the way from no solution, very slow solutions, to fast solutions.
Yeah.
So.
Yep, I absolutely agree there. Like people stating to implement the same algorithm, but big differences. Yes.
Slightly,
also in different types. There was recently a nice preprint by Fabian Fröhlich, who compared some trust region optimizers there and also concluded exactly that.
All right. Yeah. Okay.
I would say one of the other issues, going back to the question of why was this difficult, is agreeing on a subset. Like you have different tools that all do slightly different things, and they have literally different information in their input files, basically. So deciding like this, like coming up with a set of inputs that everyone's going to agree, yeah, that's good enough, is a really difficult problem.
Yeah, that's true. And specific tools have, again, some special features, applying some data normalization before. Sometimes these things are not even clearly documented, or you might even not be aware that they are happening. And these are things we didn't really include here. Might be a limitation for some, but yeah, we need to agree on a core set. You're right. Yeah, one point there maybe also we don't support currently arbitrary cost function. So you do have a certain control over your cost function with your specific noise assumptions. So whether you choose normally distributed error or log normal or Laplace or whatever, but you can't just put some arbitrary cost function there.
No, that's hard for the implementers. Yeah.
Any other questions for Daniel? Okay, there's a question. What about sensitivity analysis? Does it provide any support for sensitivity analysis?
Could you provide a bit more background? What do you mean by sensitivity analysis specifically? Like computing some, I don't know, some gradients for your likelihood, or some state sensitivities, or metabolic control analysis, or...
Can I talk? Hello? Do you hear me?
Yes, we can hear you. Go for it.
Okay, thank you. Because I was not thinking I can't talk. Okay, thank you really for all of the presentation. And so I may have just a question, because all of the model that I am seeing is a little bit, we have large scale model. That means we have large parameters, yeah? In the way that in the when you try to do optimization, we mean that we have this there is interdependence between the parameters. And we start to do one is dependent with other one answer. In this case, if we will try to do parameter estimation, you can get, it's not unique. You don't find one parameter, it's followed out. It's problem for is ill condition. This is what we say that as a mathematician is condition. In this case, I think one way how we can handle that, we think about doing parameter sensitivity analysis. What does it mean? It just, you look locally, because you give some parameters and you see how is moving, how is changing your model depends in these parameters, okay? Of course, it's local. You get some kind of information. Then, and after that, you can try to do your subsets, okay? And you do some kind of analysis in the way to find the right subset. It is the best way to be able to invert your matrix in the way that you get your parameters. You understand what I mean?
Yeah.
You're referring to gradient-based optimization?
Yes.
Pretty much, right?
Yeah. In that way. Yeah.
Yep. So as I briefly mentioned, so PTAB doesn't really care about which optimization algorithm you would use. So it doesn't exclude gradient-based optimization, but it also doesn't let you specify it exactly. So in my daily work, I do use gradient-based optimization, but you could also use some derivative-free optimization or no optimization at all, but some MC sampling or whatever.
So P tab basically specifies the inputs, not necessarily the outputs. Is that basically
exactly
it? Okay. Right.
Good. Yeah.
So it's up to the the person doing the study then to decide what kind of information they want, whether it's confidence limits or MCMC or whatever it might be, or profile likelihood or bootstrapping.
Exactly.
Okay.
So similar to SBML, like you just specify the model, you don't specify the simulation algorithm.
Okay.
Yeah. Okay. Okay. Good. Thank you. Yeah. Interesting.
This might be a question. This is a better question for Joe, but maybe Herbert would know. If anybody's interested, when SB Stoat might have support for PE tab.
Yeah, when Joe has time, I guess. I know he keeps working on it, so yeah, maybe this fall. I don't know. I wouldn't want to promise anything, but I would like to see with SB Stoat.
Like what kind of support were you thinking? Would you be thinking that SB Stoat would be something that you could create PE tab in, or that would import and export?
Import export. So you could create it, you could export it, and then you could import it. But I'd also like us to. I would also like SB Stoat to offer alternative. It doesn't implement the optimizers itself, and we found that the Python differential evolution optimizer is okay, but it's not good for big models. And it'd be nice to be able to offer more optimizer alternatives as well. So that'd be the two things to do.
We do have a couple of optimizers accessible via PyPesto, if that's something you might want to link to. SB Stoat gives you also.
Yeah, that's true. I'd have to ask Michael about that. He's the person who's been working on a lot of the trying out all the different optimizers. See which one.
We're actually not so enthusiastic about the SciPy optimizers.
No, they're not so good on big models. They work on little things, okay, but anything serious, they don't do so well.
I might have missed it on the tool support slide, but we've talked a little bit about PyBioNetFit as a parameter estimation tool. Have they mentioned any plans to support PE tab, or are they already?
I think it was mentioned that it would be interesting, but I'm not aware of any really concrete plans that
Yeah, I don't know either.
that is about to happen. Or
I mean, that's not a bad package. The optimizer is reasonably good. So
Okay, last call for questions, since we're getting close to the hour.
I would like to get some references in that stuff. It will be possible.
which stuff?
I'm talking about the way how you do the parameter estimations, the model validations, and so it's all of that. They are given in your book, in the first book that you show us in the first day.
Quite a few of them, yeah.
Okay.
Yeah.
Good. Yeah. I'm interested to that stuff in the way, because I'm a mathematician, in the way that I did lots.
Oh, yeah, yeah.
In the parameter estimation model validation with the big models, I'm using ODE, D-Day models and so
Yes.
getting a parameter, and I am going deeply in the mathematical part.
Yeah, we desperately need good, robust optimizer algorithms for big models.
Yeah, because the problem when you start to you use the derivatives, it's almost, you get a problem. You know the gradient.
Exactly.
As you are out, you will not get the best optimize. You will not able to get to.
And we want them to run in a reasonable amount of time. Not take days and days and days to run.
It's true.
Just to do one optimization when you want to do maybe 20,000.
Yeah, it's true. You have
then you got problems.
Yeah. I had a model with how many states? I think like it's not like what you have, but it's just a large one with 80 parameters.
Oh, that's a lot.
25 state, but is all interconnected very well. It's cardiovascular model.
Oh,
we need to do a lot of math, in order you'll be able to estimate the right set of the parameters. And we have some kind of stuff how we do parameters, how we do sensitivity analysis. It's local, of course. It's a local. It's
yeah.
But it gives you ideas.
Yeah.
How they are moving. This is but I learned a lot from you really this week. It was very interesting for me, really.
I mean, SP Stoat implements bootstrapping.
Yeah.
Which probably doesn't, I don't know how well it scales, but that'll give you a sort of non-linear sensitivities around the minimum.
Okay.
Which are more accurate than the linear ones.
It's true, yeah.
But they can take a while to compute though.
Yeah. But just you are using just user function. That means try to do something like automatic differentiation,
Yeah, we haven't done that. We've mentioned it. We did do it. It depends how efficient it is.
Yeah.
If you just do straight differentiation, replace this is for computing the Hessian or the Jacobian.
Yeah.
If you just replace it with the derivative, sometimes the derivative can be bigger than, can be twice as big than the original equation.
It's true. Yeah.
And then it actually slows down things.
Yeah.
So, Depends. Yeah, it depends on the problem.
Mustafa, if you're interested there in accurate sensitivities and stuff, I'm not sure if you're aware of Amici that does these sensitivity calculations like symbolically as far as possible, and works quite well also for large models.
What tool is that?
Amici. I will.
Oh yeah, okay.
Share with us. It's really isn't. I like to see really.
Yeah.
Yeah, I will post a link.
Yeah.
But I think time is up. I will post in the chat.
There's Jackie.
Thanks for having me.
Jackie.
That's help really.
Thank you, Daniel, so much for joining us this morning.
Thank you, really. Thank you.
Thank you, everyone, for contributing to the conversation.
No, it was.
All right, we're going to move on to our next talk. So I'll go ahead and share. All right, we would now like to welcome our next speaker, Dr. Jackie Snope. Dr. Snope is a South African Research Chair Initiative research professor at Stellenbosch University, as well as a professor at VU Amsterdam. Dr. Snope is a steward of the FAIR principles and developed the JWS online model database and simulator and the FAIRDom hub, which both seek to enable model sharing and management that's accessible to the systems biology modeling community, which is something we've talked a little bit about in our course. His research group combines experimental, computational, and theoretical approaches to try to understand how components of biological systems are able to drive the dynamics of the system and the functional behavior of the systems. Much of his work focuses on human pathogens, including those responsible for tuberculosis and also human disease states in diabetes and HIV, along with another number of other diseases. Recent work in his group has studied mechanisms of glycolytic oscillatory behavior in yeast, using experimental and modeling approaches. And today, Dr. Snope is going to present some of his group's recent modeling research. So thank you for joining us today, Dr. Snope. And you're welcome to share your screen and check sound.
Thank you, Veronica. Let me see if the sharing screen works. And please give me some feedback.
That
if
works.
Is
your audio is good.
The sound is good. Is this
Yep.
Okay?
Yep.
And I'm not sure how feedback comes from the students. Do you just yell, or is there just questions only at the end? It's because it's
Chat. And chat.
and chat. Okay.
Yes, chat during
I'm
the
actually, so I'm not 100% sure if I see chat in full screen, but Veronica, I can see you. If you just wave if there is a question, then I can, or maybe you can ask the question, then I can.
For me, I found that the controls at the top sort of pull down when there's something in the chat.
Yeah.
And then if you click on like the more options, you can go to the chat from there.
There.
Here, I'll type something in the chat so you can see what happens.
Lucian. Yeah. No, I can see the option, but I can't see it without using that option. And is my mouse visible? That's also something.
It is, yes.
Yep.
Okay, good. Hey, I'm already on the next slide. Let's go back to the beginning. Okay, good. Because it is important probably to give some feedback during the talk, because it was hard for me to judge the level of the students and the background of the students and so more generally the audience. So I heard in the discussion just now that there are mathematicians in the field. So I gave a talk along the same lines for mathematicians last time, and they were a little bit baffled by the dots in some of my graphs, which were the experimental measurements. So there is a lot of interaction between maths and modeling and experiment. So I'd like to focus a bit on that, and I chose as a topic synchronization of yeast glycolytic oscillations, and I think it's a very nice example of how you can go from really bottom-up studies, starting with enzyme kinetics, all the way to interactions within a community. And you might think it's a bit early for wine at your part of the globe, but I am looking forward to having dinner after this talk and pour me some wine. So the topic is roughly moving between model construction, model validation, and model analysis. I think those are really key parts in the modeling process, and I hope to be able to move through all the aspects and explain this a little bit. So let me give some feedback on yeast and yeast glycolysis. So we all know yeast because it produces this, of course, this wine, and it one of the, although not the most important component, but an important component of the wine is the ethanol, and yeast produces that from glucose in using this metabolic pathway. It's glycolysis. It consists of some 12 enzymes. And you see that each of the reaction steps is a simple chemical reaction catalyzed by an enzyme. And this provides the network that is going to be used in the model. So for this specific model, there is actually not a problem setting up the network structure, because we know the network structure through and through. So for each of the metabolites, those will be the variables in the model, and you simply set up an ODE model for each of the metabolites as a function of the rate of its production and the rate of its degradation. So what I'll start with is how we, after we've of course made this structure on ODEs, how we characterize each of the reactions in this system, and this we do experimentally. And this is an important aspect of the bottom-up modeling approach, that we can actually characterize each of the reactions individually. So I just chose as an example here the hexokinase reaction, which is the first reaction that converts glucose plus ATP into glucose 6-phosphate and ADP. And we measure now the kinetics of this enzyme in vitro. So we open up the cells and we can characterize each enzyme individually. And this is an important aspect because we can now perturb each of the variables that influence the kinetics individually. So we can saturate the reaction with glucose. We look increasing glucose concentrations, we get an increase in the enzyme activity, and the other substrate ATP. And we can also look at the effects of the products. This is an important aspect because you can make an independent perturbation for every parameter that's part of your model. And in that way, we do not run into identifiability issues if we want to parameterize the model afterwards, because we parameterize each reaction individually, and that sets the parameters. You don't have to parameterize a complete model. You parameterize each of the individual reactions, and then you simulate it. So we don't have the issues, as I heard you discussing before, on identifiability of parameters in large data sets, which don't contain enough information to find all the parameters. Okay, so this process we do for each of the reactions. So all of the reactions in the system we've characterized in this way. Then what you see, and this is, maybe I'll go back a little bit. What you see is that a substrate tends to increase the activity of an enzyme, and the product tends to decrease the activity of an enzyme. And this leads to a sort of a natural movement of the system to a stable, steady state. Because if the substrate of a reaction increases, the reaction that degrades the substrate will have a higher activity, and this will stabilize every perturbation to the system back to a steady state. So then you get this natural behavior that these models go to a steady state, which is nice for experiments because you don't have to bother about time. The system is in a stable state, and you can then easily check whether your model predicts the steady state correctly. So that's nice, but it's also a bit boring. So the more interesting aspect is the dynamics. And what we saw is that yeast also shows limit cycle oscillations. And this was a bit surprising because we've seen this homeostatic characteristics of these systems. They tend to have stable, steady states. Why does it sometimes then go to a limit cycle oscillation? And let me move to that, how that looks. And here I show a time trace of a yeast population where we can observe oscillations in an intermediate. And so we don't have to open up the cells. This is a direct observation in intact cells. And that's possible to see this via autoimmunofluorescence of the NADH in the system. So NADH is one of the variables in the system, and we see that it oscillates. Now, this might not look so surprising because we've all seen oscillatory systems, but you have to realize there are millions and millions of yeast cells in this incubation. And in order to see an average signal, the yeast cells must be synchronized. Right? If everybody oscillates on its own, there will not be an average signal and you wouldn't see anything. So the cells need to be synchronized. So let's see if we can figure out what's the mechanism underlying the oscillations, and then also to see, can we figure out why they synchronize? So as I said, most of the kinetics look homeostatic. So a substrate tends to increase and a product tends to decrease. But there is one reaction where we see a different type of kinetics, and that's the PFK. It's a phosphofructokinase. It catalyzes the third reaction in the system. And what we see is that ATP, which is a substrate of the reaction, tends to inhibit the enzyme at higher concentration. And that inhibitory effect of ATP tends to become larger at smaller concentration of the co-substrate, fructose 6-phosphate. So here is the fructose 6-phosphate concentration. If you decrease that concentration in the incubation, you see that ATP very rapidly starts to inactivate or inhibit the enzyme. So we've characterized this enzyme very thoroughly, and you will see I will keep on coming back to this to this enzyme. And we thought, okay, can we get the stable oscillatory, the stable steady state model? Can we calibrate it to some extent such that we get limit cycle oscillations. And that's a tricky aspect. And I think there is here's a little bit of mathematics to see how to do this, because how are you gonna get a model to oscillate? Because you will see if you give a model just some oscillatory data, it will very quickly decide to go through the average, right? Because that's a pretty good description. So it won't oscillate. So what we decided, okay, let's see, we're gonna give the model some leeway that we think we are pretty close to the correct solution. But we're going to allow a little bit of parameterization, a little bit of leeway to change the parameters, but we put a cost function on that. And then what we found is that with very limited information and a good objective function, we got the system to oscillate very quickly, and it showed remarkably close to the experimental data. So what the objective function, we went through 3 steps to the optimization, the calibration of the system. First, we tell the cells, you oscillate, the system must oscillate. And we did that by saying, if you go from a steady state to a limit cycle, you must go through the Hopf bifurcation, right? And the Hopf bifurcation is you can find that, so that's just a bifurcation point where you go from a stable steady state to an oscillatory range. You can find that by looking at the eigenvalues of the Jacobian. And what we told the system, we're going to optimize. So we're going to look at what parameters or what rate equations lead to an increase in the ratio of the imaginary part of the eigenvalue over the real part. Because at the Jacobian, the real part of the eigenvalue is 0. So, or close to 0 if you approach that point. So by optimizing, by maximizing this ratio, we got very close to the Hopf bifurcation in just a number of cycles. This was a very powerful objective function. And I will mention that a couple of times later too, is that for us, the formulation of the objective function is much more important than the method you use to actually find the objective function. And in papers, often people focus so much on what is your method. So do you use steepest descent of Levenbach-Marquardt or something? We found that was actually completely irrelevant. If you define the objective function well for the problem, we could simply use steepest descent. It worked pretty good. If you then want to get like better, you can then after the steepest descent do a Levenbach-Marquardt, which then gives a bit closer answer. But the thing is, with these optimizations, you get what you ask for. So we got close to the Hopf bifurcation, but since it's a supercritical Hopf bifurcation, you have an amplitude that is very small. So we had to give a little bit more information to the system. We also gave it the amplitude of one of the variables in the system. So this was fructose 1,6-bisphosphate. This has the largest amplitude. So we say this second step of optimization is to pull the system through the Hopf bifurcation. So not only to oscillate, but also with a sizable amplitude. And then the last step for the synchronization is that here we optimize the integral of the product of an intermediate and 2 cells. So if the 2 intermediates move together, the product will be the biggest. And if you integrate that over a period, this is a fairly simple system or objective function to find the synchronization. And this worked. We published this in the paper some years ago. It actually was 3 back-to-back papers to move through the whole process of the model construction and validation. So this was the answer we got from the optimizations for the oscillations. The dots are then the experimental measure points, and the lines are then the model simulation. And it's quite remarkable, I think, that you get a correct answer for many features that you didn't optimize for. So for instance, the frequency is quite good. The phases between the different metabolites is good. And some of the amplitudes are also fairly good. So this one not so good, but this one was given, so that's not a validation, but many of the other ones were quite close to the experimental observations. Now here we check for the synchronization. What we do here is we have these lines here is a mixture of two populations that are 180 degrees out of phase. And then you mix these two populations. And then because the oscillations are close to sinusoidal, you see that the amplitude at the beginning is small because you average out the signals from the two populations, but they fairly quickly, within 7 or 8 sweeps, start to synchronize with the sizable oscillation. We also tried this with the model. In the model, the oscillations are not purely sinusoidal. So even if you mix two cultures 108 or close to 180 degrees out of phase, the amplitude is not completely zero, but we see a good synchronization of the populations. Now it's then important to look at what did now actually change during the optimization of the model. And what we saw is that we could, so the model has 100 parameters. It's a fairly big model, and only 5 of those parameters we needed to change with the value more than 20%. So all the small adaptations were smaller than 10% actually. But 5 we needed to change a bit more. And of those 5, no, it's 7 we needed to adapt more, and 5 of those 7 were related to the PFK kinetics, showing that enzyme is really important for the oscillations. Now this is the sort of a profile of the activity of the enzyme. So the z-axis is the activity of the enzyme, and then we have here the one substrate and there the other substrate. So we see the ATP inhibition is there in the original model. So this is the original model with the steady state here. This is after the first step of optimization, where you see we have now a trajectory. So there is a small oscillation, but it's a really small amplitude because we are close to the Hopf bifurcation. But you see that the product inhibition has become much stronger in this part than here. And then in the final optimization for the synchronization and the amplitude, we see now we have a much larger amplitude of the oscillation, and it's also the substrate inhibition has become even more pronounced. So this was a calibration of the existing model, and you can say, but why do you calibrate? You've measured all these enzyme activities. That's true, but the enzyme activities were measured in a different strain. They were measured in a production strain that doesn't oscillate, and we wanted to see, can we use it as a starting model to simulate the oscillatory behavior? So we allowed for small perturbations, were actually fairly small changes in the enzyme activity. And we gave it a very small experimental data set, right? So we just told them, you must oscillate, you must synchronize, and we gave it an amplitude. That was all. And that gave a fairly good description of the data. But of course, now we need to validate the data a bit more. So we tried all sorts of different experiments. If we could simulate a lot of different experiments that exist in the literature. That's published in the second paper on model validation. And here is a prediction for the Hopf bifurcation. So what you see here is the experimental data, and that is determined by a group in Denmark, where they vary the glucose concentration in the medium, and then they look at the amplitude of the oscillation. On the left of this point, there is no oscillation, so it's just a steady state. So there is then, of course, no amplitude. But then you see that the amplitude grows quickly if you move through the Hopf bifurcation. So from the steady state, Hopf bifurcation to the right. And here is the bifurcation plot of the model, where you see, okay, it's I would say fairly close to the Hopf bifurcation that is measured experimentally, given that the model doesn't know about the data, right? It's a prediction. Here are some other validation steps that we did, is that if you work in a continuous system and you increase the influx of substrate, you get different dynamic behavior. So at low flux values, so in the top there is low flux values, you see that the simulations as well as the data look fairly sinusoidal, right? It's a simple harmonic oscillation. If you go a little bit faster, you see that you get this relaxation type of oscillations, where you have a slower phase and a much faster phase in the oscillations. You see that in the model and also in the data, but you see it doesn't look exactly the same, right? It looks as if it's mirrored. If you go to even higher fluxes or influxes of glucose, you get this even more complicated oscillations, and as well in the model as in the experiments. The last type of validation is this showing of quenching of the oscillations. So if you at a certain point in the oscillations, sorry, here is it, you can add a bit of acetaldehyde in this case, and that acetaldehyde is one of the intermediates in the extracellular medium that has a strong effect on the synchronization. So what you can get is that if you add that acetaldehyde at the right moment, you quench the oscillations. You see that a little bit stronger in the model as in the experiment, but that works pretty good. You can, but it's only sensitive if you give this injection at the right moment. So it's very hard to do this experimentally, right? In the model, it's fairly easy to figure out where the quenching works best. And the same you can do for glucose quenching. So I think a fairly good prediction of these experiments. And now let's now go to the last part of my talk, where I try to come to the mechanism of the oscillations and of the synchronizations. And to figure this out, it was important to look at in isolated cells, because in the population of cells, you can only study the oscillations if they are synchronized. And you need to move them to single cells to distinguish between cells that are oscillate and not necessarily synchronized. Right? So to make that a little bit clearer, I made a simulation where we have two populations of cells. Each of these has the model, and the one on the right, these cells synchronize. And you see that I plot the average signal on the bottom, as I call it. On the left, they show the same oscillations, but they don't synchronize. So you don't see any average signal on the left, while you see a clear signal on the right. So it might be that even if you don't see a signal, the cells might oscillate, right? So you want to distinguish between the synchronization and the oscillation. And to do that, we work together with a group in Sweden, which have a nice access to a microfluidic chamber. So what this is a specific chamber here that is set up in a fluorescence microscope system, and you can perturb the chamber via injection speeds, and that is shown here. Is the microfluidic chamber enlarged, where the cells are positioned in this square, and now the environment that the cell sees you can influence by changing the rates of medium influx through these 4 channels. I show that here. If you have a high flux through this channel, that's what the cells see here. If you increase the flux through this channel, they will see that medium there. So you can make small perturbations to the cellular environment and look at the effect. And here is then the positioning of the cells in this microfluidic system. And we've positioned them far enough away from one another such that the cells do not affect each other. We have a fairly strong convection term through these through the microfluidic system. So the cells don't communicate with one another, but you can still observe them. And that's shown here. So each of these dots is a cell, and you can now look at the fluorescent signal in each of the cells. Here I do then I look at one of the cells, the signal. And so you see some oscillations, but they are not synchronized, right? But now, if we now perturb the acetaldehyde in the extracellular environment, and we propose that as the mechanism of synchronization, then you see then via the perturbation of the acetaldehyde, you can synchronize these cells. They synchronize according to the extracellular acetaldehyde concentration. Okay, then we looked at a couple of experiments where we compare now the behavior of a population. Then here, again, this is by the Danish group in Copenhagen, where you see that there are 2 hop bifurcations, and this is now looking at the perturbation with cyanide. You need a certain concentration of cyanide for the cells to synchronize, and at too high concentrations, they don't synchronize anymore. So there's 2 hop bifurcations, and here's the prediction of the, here is now the experiments for the single cells and the model simulation. So we took the same model that we used for the cell extract and that I talked about before, and it could simulate these experiments, not perfectly, but fairly close. And here we see that there is also two hop bifurcations with cyanide, but at a different range, right? So what you see is that the cells oscillate over a much wider range of cyanide concentrations than that they synchronize, right? So this is in the population, so you can only observe synchronized cells over a narrow range of cyanide, while the individual cells oscillate over a much wider range. Now we can also look at frequency response here. And I'll just show this as a function of glucose and cyanide. There's not a strong effect of cyanide on the frequency, but the glucose concentration at low concentrations leads to an increase of the period. So the frequency goes down at low glucose concentrations. Now let's move to a little bit of model analysis. And I realize this moves a bit fast maybe, but what we try to understand now is, can we understand such behavior as the presence of 1 or 2 hop bifurcations and the frequency effect if we just look at the phosphofructokinase? So I now look at 3 reactions that are 3 variables that affect the phosphofructokinase. It's the fructose 6-phosphate concentrations, that's one of its substrates. It's ATP, that's the other substrate, and fructose 1,6-bisphosphate. And what we now did with the model is we scanned this whole box with variable concentrations, and then look at the state of the system. And so we made very many perturbations, and each time we look at these 3 variables and then look at, do the cells oscillate or not? And what you get is this sort of a 3-dimensional cone where the cells oscillate. So although this model has like 15-dimensional, I can tell you on the basis of 3 dimensions, these 3 variables, whether the system will oscillate or not. And I found that very insightful, because that 3 dimensions I can deal with. I can even make a plot. 15 becomes too much. And now, if you now zoom a little bit on this cone, here are 2 perturbations that we can do. This is the glucose perturbation, and then you move into the cone. And the color here is the frequency of the oscillations. So what you see is as these 3 variables not only define the area where you have the oscillations, it also says you have only 1 hop bifurcation because you move into the cone, you never get out. And you will have a frequency effect, right? As you see as you move through the different colors. This is the cyanide perturbations. And you move so like more transverse through the cone. So you go in the cone and out of the cone. That's the 2 hop bifurcations. And there is only a small effect on the frequency because you stay in the same color area. So I find this really insightful. It's the combination of the math, but also then bringing it back to the enzyme kinetics to understand what's going on. Here's a plot of a phase response curve. That's another typical sort of analysis you can do with oscillatory systems, where you give a perturbation to a cell in its at different positions in its phase. So we define, so you look at a period on the x-axis, and now we make a small perturbation. So we add a little bit of acetaldehyde, and then we look, how does the system change? And what we see is the red line. So each dot is an individual cell, of course, an isolated cell. The red line is just the standard model as we've published, and you see, okay, that predicts that area quite well. And the gray zone gives the space that you occupy if you allow for a 10% parameter variation. Because these are individual cells. Each cell is a little bit different, so they definitely show heterogeneity, as you also see in the data set. And you can see that here you have also, in this phase response, you can have a type 0 response. And that's why you get this apparent discontinuity in the signal, where you move to the very high or a very low, a positive or a negative phase shift. And what we found is, upon analysis of these phase shifts, is that the acetaldehyde is indeed changing the phase in the correct direction to promote synchronizations. So then we went again to look at the mechanism in the cell. So here is this glycolysis pathway. How does acetaldehyde work? Acetaldehyde, it diffuses rapidly through the membrane, and it affects the last reaction. So what you get is a very fast cofactor response. So acetaldehyde increases the activity of the ADH, and ADH gets oxidized, leading to an increase of NAD, stimulating an GAPDH, and that has an effect on ATP. And this is a very fast response. These cofactors, they are turned over 10 to 100 times per second, because there is a fast flow through the system and the concentrations of these conserved moieties is low. So you have a fast cofactor response, and then the ATP has a slow effect on the kinases. And so there are three kinases, and you have a glucokinase, PGK, and the pyruvate kinase. In what we saw is that the PFK is very important. So that's why I showed this red line, because it's the one that is inhibited by the ATP increase. So we tested this in the model, and indeed, if we change the phosphofructokinase, if we increase the activity, the system responds much faster upon a perturbation. That's shown here by showing the order parameter. So if the order parameter is close to 1, it shows oscillation. What synchronization? But what we wanted to show here is that it's constant, and what you see is that it moves much faster to a constant signal in the order parameter at high PFK compared to the low PFK. All right, so let's now move to the last and I think quite exciting stuff. This we published this year in PNAS, where we now look at the microfluidic system, where we change the system now such that we get interaction between the cells, right? So we now make a very dense group of cells, not the widely positioned individual cells as before. And crucial is because we need the cells to communicate. So we can't have a high convection term moving the communicating agent away. So we make this reaction diffusion limited. And so the substrates diffuse through these fine channels. And this is of course reminiscent of organ structure in our body, right? Where the perfusion with blood also often works with a sort of a similar system like this, with the final states being diffusion limited. What we saw is that the cells in different positions in that chamber respond with a long delay that is much before we see the oscillatory system oscillatory signal in each of the cells, and that delay is much longer than you would expect on basis of diffusion. So it's really the communication of the intracellular oscillations to an intercellular synchronization that takes some time. So let's look at another movie where we look at the system. Now you see each of these individual cells, you can follow the NADH signal, and now and you see that there is not a total synchronization, but you will see at some point that you now and here that there is a sort of a wave signal going through these through this population. So we analyze that by looking at the cell-cell coupling, by looking at the phase, the similarity in the phase, which we again analyze via the order parameter, and we can analyze the instantaneous phase by looking at the Hilbert transform of the signal. And what you see is that under this signal here is you see that the order parameter is close to 1. So it looks at as a fairly synchronous response of the cells. And if you now work at in this case, higher cyanide concentration, you see that the order parameter becomes much smaller, and it doesn't stay for prolonged periods close to 1. So we analyze these responses by looking at the interaction between cells. So we analyze the how strongly we see a connection and define that connection and as the similar phase responses in the cells. And then we can define these communities. And this is just an example of how that's defined. And then here we show now the communities for the real experiments in an adjacency matrix. And then what we saw is that at the optimal conditions for the oscillations and the synchronization, we get 3 defined communities dependent on the position in the microfluidic chamber. And if we go to higher perturbations, we see that it becomes less or completely random, that you don't see any communities anymore. So this was quite interesting, that you can do this graphical analysis to identify communities. And here's again the simulation. So each of these little dots has that detailed 100 parameter 15 variable models. And we analyze this in a COMSOL environment to deal with the partial differential equations that we need for the cell-cell interaction. So to model the convection term and the extracellular metabolites. So each of the cells intracellularly is modeled as a well-stirred reactor, just ODEs, and the extracellular environment is modeled in COMSOL, because that was the environment that made it the easiest to correctly define the microfluidic chamber in that environment. And what you see is that, for instance, in this cell, that you see this clear, well, it's not finished, the clear movement of these waves through the population. So we analyze that a bit more in detail to look now at the autocorrelation function. Now we look at, if you have this one community, how are all the cells in the different cells in that chamber connected to this phase? That's shown here. And then what was interesting is to look at the wave velocity. That's shown here as a 1/v, which we found as and I actually calculated here. So the wave velocity in the experiment was 3.5 micrometers per second, while in the simulation, so completely independent, this is just the same model that we derived earlier, is 3.1, which we found fairly nice in agreement. All right, that was a long story, but I summarized it here a little bit to say how we started with isolated enzyme kinetics. And we could see that you could get the oscillations by making small perturbations only to the model parameters. So and I think important here is that the calibration was driven by how you define the objective function. And maybe that works with such a simple method for the optimization because we were already fairly close. So it does pay off to really characterize the model for the individual steps correctly from the beginning, because then you don't have to make any big changes later on in the modeling workflow. So we could show that the ATP AMP mechanism, which was originally proposed by Goldbeater, seems to be working for these systems fairly well. And the last parts were done on isolated, so individual cells, which gives a better resolution because you're now not limited only to the synchronization environment, but you can directly look at the oscillations in individual cells. Good, and I think I spoke maybe a bit too long, but I hope there is still some time for questions. Well, let me thank, maybe a bit important. The original work of model construction was done in Amsterdam together with Hans Westerhoff and some people in his group. And the isolated cells, so the individual cell work was done in the group of Matthias Goxor at Gothenburg University. And in Stellenbosch, we've done most of the modeling, definitely on this last part by a PhD student and a close collaborator, Van Niekerk. And we've been having good discussions with Albert Goldbeater on the oscillatory mechanism. Thank you for your attention. I hope I did not completely, maybe I put in a bit too much, but I hope some of it came through and we can have some discussions.
I think this was an excellent example of starting with a relatively small component of the system and adding layers on that over time. And really nice to see how, like, we were hand in hand with the experimental and computational approaches. Does anyone have questions for Dr. Snope? You're free to unmute yourselves if you want to ask them.
I have a question regarding the spatial diffusion. I think that was the slide with the animations. So how do you get that one?
This one? Oh, okay.
How you set the constraints for, because as far as I know, you're using, well, I understood that you're using a partial differential equation, but how do you set the shape of this particular shape with the equation?
Yeah, so we did this in a specialized simulation environment. It's called COMSOL. It's specialized in these types of simulations, and the trick is how to. So you use finite elements to define the to define the area where you do the simulations in, and this is not a trivial task. How to set up your finite elements, because you want to make them as big as possible so that you don't go crazy in the calculations, but you can't go too big because you don't want to lose precision in the simulation. So we let COMSOL, so you define you can just make an AutoCAD drawing and you put it in this COMSOL, and it will define the finite elements. We've also tried this in Mathematica, trying to do it ourselves, but that doesn't help in speed. It's quite hard to define the finite elements in a way that you've these simulations. I think they run overnight, right? So it takes quite a bit of time to do the simulations with the PDEs, because we have about 100 cells, and each cell has that detailed model. Yeah, so that in combination with the PDEs in the extracellular environment makes it computationally quite hard. Does that answer your question? So you define the architecture using finite elements.
Yes, it does. Like, one more question: is this library open source, or do you have to pay for it?
Now the COMSOL is quite expensive, so that's well, for South African. I mean, Herbert with his institute has money galore, right? So, but
if only.
Is that COMSOL? Is that?
Yeah, correct.
Okay.
Yeah, it's a well-known environment. It's pretty cool. Yeah, and you can do these without all the fancy extra libraries for which you have to pay. The standard feature does it.
Yeah, we actually used this paper as well for our journal club actually a couple of months ago. So I guess one question for me is, I mean, you built up this story, this over the many years. It's quite a remarkable story. Where do you see it going further? Do you see any more work here that you might find interesting?
Yeah, so what I'd like to do is to use this. I mean, that's how I actually sold it for my grant to work on diseases and the whole body systems. Is that we're going to use this as a model system for modeling, so spatial differentiation in organs. So whereas dependent on the positioning of the cells, you get different behavior. Even in steroid biosynthesis, we've shown this quite nicely, and I want to directly use that. So I have now a student that goes to Sweden to look at beta cells in such an environment. And then we look at glycolytic oscillations and insulin production. So I think the yeast system is, as far as I'm concerned, finished. I don't think we can do much more in the yeast system.
Okay.
But for these mammalian systems, particularly the insulin signaling, I'm quite intrigued to see. We all know that if you increase the glucose concentration, that the insulin concentration goes up, and this increases the glucose consumption. But it's not so well known that insulin concentration actually oscillates. So
Oh, I didn't know that.
and it seems that the oscillation in the insulin production are linked to the glycolytic oscillations in the beta cells. So beta cells are the cells in the pancreas that make the insulin. So I would be interested to study this and see how it has changed in type 2 diabetes patients.
Oh yeah, okay.
But it's been 20 years, right?
Yeah.
That first model, the Thursing model, was published in 2000.
Yeah. Yeah. Takes time.
Yeah. So I don't know. Was the talk a bit too fast, maybe, or too detailed? Too not enough modeling? Too much experiments? What?
No,
Yeah,
it's
Jack,
fine.
the talk
All
was
of
great,
this
Jack.
was really incredible. I do have one more question regarding like the partial differential equation that you used. Are you considering like a simple wave equation, or like if someone would try to do this, like in a Python module, what general the ODE PDE you would recommend to use to simulate all this?
Yeah, so the PDEs are only for the extracellular environment, so that's pretty straightforward. It's just diffusion. It's like it's the diffusion equation. So if as a function of the diffusion coefficient and the concentration gradient, that defines the speed. There's nothing fancy about the PDEs. I think the fancy part comes a bit in the defining the finite elements to simulate the architecture, but otherwise this is pretty straightforward. The tricky part is the intracellular, and that we had already developed over so many years. So we didn't change a single parameter to simulate this environment. Right? We kept the model as it was.
Yeah, I mean, I guess the only complicated bit here is if you want to mimic this shape that he's got, that'd be the tedious bit. But you could easily do, you know, a rectangular spatial surface in Python.
Yeah, I've now actually started doing so, looking at movement of single molecules in yeast cells, where we look at cell cycle behavior. So and then look at movement of single molecules. And this is very nice. And we do this also in a similar way, where we actually from a microscopic image we can analyze where are the individual molecules, and then also where is the cell. So I've written some code to analyze these images and get the precise cell image in 3D, and then from that we define then the boundaries using a mesh structure in Mathematica, and use that directly in the PDE simulation. And this is pretty cool. It works actually. You can simulate precise cell that you see in the image. So
it seems it seems that so with a metabolic pathway, you and other groups have shown that you can just recalibrate the enzymes and the physiological conditions, and the models are pretty good. Now you can't do that for a signaling pathway because we don't. It's it's not quite the same as a metabolic pathway. So I'm not sure how would you build a signaling pathway in a similar way? You probably couldn't, could you? You'd have to do just brute force fitting and measuring of all the species.
So we did this for the insulin signaling pathway in muscle cells because we are obviously studying type 2 diabetes, and we wanted to get a good model for the insulin signaling. And the crucial part is not to make a new model on insulin signaling, but how to link the insulin signaling to glucose transport and then to metabolism. So to connect the different modules. And the signaling part, so what you do is you follow the phosphorylation of the individual components in the pathway, and then you can look at a steady state behavior where you do a dose response curve. So you look at what is the extent of phosphorylation of the different components as a function of the insulin at steady state. And the steady state defines then the a constraint on the K on and K off. And then and then what we did is then we did the dynamics. So we did then follow the time response of the on and off. So when you give insulin or when you take the insulin away, and those then define the absolute values of the on and off. So and that worked pretty good. It's tricky because you can't isolate the components and characterize them. But we used then simple kinetics, so it's mass action kinetics.
No, I see.
And then by using this trick, first analyzing the steady state to define a constraint on the parameters, so you know the ratio. And then look at the dynamics to figure out what are the individual ones.
Huh. That's an interesting way of doing it. Okay.
I think we might have a question from Andre, if you still have a question.
Sure. Jackie, great talk. So just two questions. One is a bit more about the finite elements. So how many are there actually in per cell? I mean, because you would have to have, I guess, several hundred at least, but probably more, right?
Yeah, so I might not have explained this properly. So each of the circles you see here, right? Each of them is a cell. So each of these cells have the full kinetic model. So each of these have the 15 variable models with the 100 parameters. So the complicated model. The finite elements we only defined for the microfluidic systems, the extracellular environment. So we model the cells, the intracellular. So the yeast cells, the yeast cells are modeled intracellularly with ODEs, and the extracellular environment is modeled with PDEs. Right. So, and right. I'm honest, I don't know how many finite elements we define. It's a lot, I can assure you.
And the exchange between the intercellular and extracellular, I mean, which of the species, you probably said this, but I probably have missed it. So which of the species actually?
It's very detailed, of course, with if you're not familiar with this, but it's the acetaldehyde. So right. it's an intermediate. It's interesting. It's the intermediate for the last reaction, and like ethanol, acetaldehyde moves very quickly through the membrane, and that allows the synchronization. That's also the metabolite
that time synchronization between your two different sorts of simulations, and did you have to experiment with what the best like differentiation was there? Like you update your cell and then you update the environment, or do you do it all continuously? Or
here it's continuous. So the and honestly, I don't know the real intricate details of the integration in this console environment. It basically worked, but what was the biggest issue is actually how to. The interface is not so nice. So how do you define these 100 models in these 100 cells? And in Mathematica, I can do that with a few lines, right? You just make a table. But in Console, you had to do this copy paste. It was a bit of a pain. There was not a good interface to define 100 different cells.
It's interesting.
So, but the simulations work nice. But what was important, because it looks now, this was not the first design, right? I can assure you, we struggled a bit to get the synchronization going, because in these microfluidic systems, the convection term, so the flow of the medium is always so high that you struggle to get synchronization. And you can't switch the flow off, because then you get an ill-defined system and the cells don't have any food. So now how to define the environment where you have the biggest chance to see the synchronization. And then we came up with this, okay, we can't use a convection term, so we must do it with diffusion. And you must then try and make it such that the that you get a group of cells that see the same thing. So that's why we came up with the circle setup with the diffusion channel.
Oh, yeah.
Tellurium had a question. She said the movement study would be really interesting that you described. Would you stain the cells in that case for tracking movement?
Sorry, I'm not sure if I understand the movement.
Maybe Tellurium, I don't know if you want to expand on your question. I think when you were describing how you would expand this model system to other systems that you talked about, I guess like some other applications of the same
organs or something, perhaps.
Yeah.
Just,
So
I
the
guess
organs.
just asking about
yeah.
the experimental details of that.
Yeah, it's no, that's a very good question, because we have some information on. So we also model steroid biosynthesis in adrenal systems, and there we know that you have different layers, cortex and different layers in the adrenals, and the steroid biosynthesis is a very complex pathway. It has so many branch points and parallel routes, and dependent on which of these branch fluxes are used, you produce different steroids. And what we see is that the different layers produce different steroids while they all have the same biosynthetic pathway. So what we would like to do is can we use a similar system like this, and on the basis of diffusion, because all these steroids, they go in and out of the cells easily because they are also very hydrophobic. So they move through membranes easily. Can we simulate the observed steroid production rates that we know happens in the organs? But your question is very good, because we cannot look inside the individual cells. So it would be more like a sort of a can we do it type of modeling approach. It's going to be hard to validate whether the model is correct, because we don't have information on individual cells. Like here, we are lucky that we can look at NADH, which we can observe in intact cells via fluorescence. We don't have such a trick for the steroids.
Any final questions for Dr. Snope? I think we're coming up at the end.
Okay, I think I'm gonna get ready for my dinner and a glass of wine. Well, you still have a long day ahead of you. Is this the last day of the mini course?
Yes, this is the last day, and this is a symposium day, so yeah.
Okay. I glanced through some of the presentations. I saw they were available. So I looked at the first one that Veronique gave and glanced through the. It looked interesting. So how many participants? I can't even see how many people are in this talk. But how many participants did you have in the workshop?
Right now there are 25, and we've had close to 40 or around 40.
Yeah.
That's a nice, and it's completely online, the whole thing?
Correct.
Okay, so there's no experimental component, is it?
No.
The whole thing is an experiment.
We did have a lot of questions about experimental details, and I think your talk was the first that really touched on the experimental side. So it's really nice to have that perspective.
Yeah.
Yeah, I try to always emphasize this, that it works together. It's hard to model without experimental data, and without a model, it's very hard to make any sense of experimental data if you want to come to an integrated analysis.
No.
And I think that in iteration, it's not often emphasized enough. I think it's really important.
Mm-hmm.
Well, thank you so much for joining us, Dr. Snope. I hope you have a good evening, good dinner.
Thank you for the. I will. But thanks for the invitation. Also, thanks,
no
Herman.
problem.
I enjoyed. Yeah.
Yeah, no, this has been good. It's been a very good morning. Yeah, we got another 3 coming up. So.
Okay.
Yeah.